This is an example of a problem on the AC Mesh Solutions tutorial in Circuit Tutor on level 3, or the hard level. As always, we have examples available in multiple levels of difficulty, and it's recommended that you look at some of those prior to trying to solve the problems. Okay, so we're going to go into this problem at the hard level. And notice that the mesh currents have already been defined for us, and in particular, by default, the program has been taking the outer mesh as the reference mesh. So the outer mesh current, which would go counterclockwise here, has been defined as being 0. So the only mesh currents are those shown that are non-zero, I1 through I4. Okay, because this is a solutions game, the KVL equations have already been provided for us for the super meshes that are involved in this problem. So we do not need to find those. We do, however, need to find the current constraint equations for each of the two current sources in this problem, which happen to be independent sources. And also we have two SOT variables, namely a SOT voltage V0 across this 8 ohm resistor and a SOT current I0 through the inductor here. So let's go ahead and do that to start. So let's write the current constraint equations, and let's do the I1S source first. And notice that we have two mesh currents passing through that source, namely I1 and I2. So we will need a difference of mesh currents, and that will be equal to the fixed value of that independent source. So now, in looking at these directions to try to get the right polarity, we see that I1 is going clockwise, so it'll be going down through that source, which is in agreement with the direction of the current arrow. So therefore the I1 will have the positive sign in this difference, and then I2 is traveling clockwise in this mesh, and therefore up through that current source, which is opposite to the defined reference direction. So it will be minus I2 in that difference. And then the value of the I1S source is found down here. It's 5 angle 180 degrees. Now you may know that 5 angle 180 is the same as negative 5 in rectangular coordinates, or rectangular form of the complex number, but this is the polar form, and in the polar form you cannot enter a negative 5 here, for example, because magnitudes of a complex number, which is what this is, are always by definition positive, so that'll give you an error. You could, if you wanted, put a minus sign out here instead of the 180 degrees. You could change that to 0 degrees and put a minus sign out here, but we'll just leave it like this for now. Okay, so that is correct. And secondly, we need to write a constraint equation for the second current source, I2S. And once again, that links actually two different meshes, I3 and I4. So we will once again need a difference of mesh currents in this problem for that current source, and that will be equal to, again, a fixed value of that current source. And I2S is 7 angle minus 105 degrees, so we'll just go ahead and put that in there. And then again, checking polarity, we see that I3 goes clockwise, therefore down through this source, which is in agreement with the reference direction of that current arrow. So therefore I3 will have the positive sign here, and we will be subtracting the I4, which is going up through that current source, which is opposite to the direction of the reference arrow. So that has to have the minus sign. There's always a difference in mesh currents if they're consistently defined, as Circuit Tutor does, all going in the same direction here. Except, of course, as I said, Circuit Tutor actually doesn't handle outer mesh currents right now, but if it did, then that would be going opposite. Okay, so that completes that equation. Let's check that. That is correct. And finally, we need a couple of SOT variable equations. So let's do V0 first. That's a SOT branch voltage because it appears across a single element. So we will select SOT branch voltage here on the drop-down. And then we have V0 equals. And now we observe that there's only a single mesh current going through that resistor. Since we've defined the outer mesh current that would go in the opposite direction as 0 as our reference mesh, there's only one, and therefore we need this type of term, which, as you can see from the tooltip, is for voltage dropped across an impedance that has one non-zero mesh current. And that mesh current, of course, is I1 there. And then the value of the resistance is 8 ohms. Now we, however, as always with Ohm's law, or the vehicle's I-Z relationship more generally in AC circuits, need to be careful about polarity, that famous P word that will always cause errors if we don't pay attention. So here we notice that this I1 current is actually going into the negative sign of the defined voltage V0, and therefore that's the active sign convention, which means we will need a negative sign in the Ohm's law equation. If we put a plus sign, that will be incorrect. Now, if the defined polarity of V0 were reversed here, then we'd have a plus sign, but in this case we have the minus sign. So let's check that. That is correct. And then the other SOT variable is a current through the inductor, so that's a SOT branch current. So we'll select that palette of terms. And we have I0 equal to, and now we notice that that inductor actually is linked by two mesh currents, I2 and I3, so we will need a difference of mesh currents here, or this term. I mean, you could use two of these terms if you like with the appropriate signs, but it's probably easier just to use this one. Okay, so in that case, we notice that I3 is going clockwise here in mesh 3, so it's going to go up through that inductor, which agrees with the defined reference direction of I0. So therefore, the I3 has the positive sign here, whereas I2 is going clockwise or down through that inductor, and that's opposite to the reference direction of I0, so I2 is going to be the one that has the negative sign. It's always going to be a difference of mesh currents, except of course if you're on the outer mesh, since the outer mesh current is 0, therefore one of the items in the difference would be 0. Okay, so we check that, and that is correct. And now, I believe we've written all of the required equations. If you wanted to check whether you have enough equations or not, which is oftentimes a good thing to do, you could simply count. So ignoring for a moment the SOT variable equations, we have 1, 2, 3, 4 unknowns. There are no control variables in this case because we have no dependent sources. So just 4 unknowns. So we would need 4 equations, and we have 1, 2, 3, 4 equations. So that is a sufficient number of equations, assuming, of course, that they're linearly independent of each other, which they are. So now we'll click No More Equations. And this is where sort of the new part starts in the solution game, which is that we are going to actually have to solve these equations now. And we're going to begin by solving these first 4 equations for the 4 relevant mesh currents, and then from those compute the SOT variable amounts. So before we do that, we're going to put these 4 equations into a standard form, just to make it easier to solve them, by combining the coefficients of each variable and putting any constants over on the right-hand side, as one normally does in a standard algebraic form. We are allowed, if we needed to multiply or divide by a constant here. I don't see any real reason you would want to do that in this problem, but I suppose if you had every term with a constant factor or something, that might be useful. But we're not allowed to, for example, substitute this equation into one of these or anything of that nature. There's no linear combinations allowed. We'll do that only when we're solving the problem after writing these equations out in standard form. Okay, so we're going to enter that here into this form. And again, we have 4 slots, 4 rows in the form for each of these 4 equations. So the first one, I'll just put these in order for simplicity. So we have I1 minus I2 is 5 angle 180 degrees. So I1 will have a coefficient of 1. And the I2 will have a coefficient, of course, of minus 1, because that's being subtracted. And then the 5 angle 180, we'll go over here and put that as 5 180. We could equivalently, I suppose, put negative 180, but since it's written that way, we'll put it this way. Now remember that the coefficients on the left-hand side are always written in rectangular form, as it says here. On the right-hand side, however, you can see that the blanks are intended to be used for the polar form. So I could not, for example, enter negative 5, even though you may remember that 5 angle 180 is in fact negative 5 in rectangular form, because 180 degrees, if you draw the Argand diagram with the unit circle and the complex plane, negative 1 would be over here on the negative real axis, and that's an angle of 180 degrees from the positive real axis, which is our reference. But we have to enter it this way. Okay, so the next one is I3 minus I4. So we can have I3 times 1. There's no I1 or I2 in that equation. And then the I4 would have the negative 1. And then we need, again, the constant term, which is the 7, the source value, which is 7 angle negative 105. So the next equation is this third one. And here first we look for the coefficients of I1. There's only one term involving I1, which has a coefficient of 8. Of course, dropping these units now. We don't put any units in these text boxes either. So that would be 8, as it says here, numbers only. And then I2 has a coefficient of J5, as we see here. So we just type that again in rectangular form. And then I3 has a coefficient of negative J5, as we see here. So we just type that. And then there is no I4 term. And the constant term here, if we add the two angle 0 to both sides, then that'll put it over here with a positive coefficient. So we have 2 angle 0 degrees. Okay? And then the last equation, there's no I1 here, so we have nothing there. I2 has a coefficient of minus J5. And the I3 has a coefficient, just the one term here, of J5. And then I4 has a coefficient, just the one term here, of minus J8. And then this constant we'll subtract from both sides. So, and in order to do that, remember that I cannot put a negative sign out here. There's no place to put a negative sign. So in order to make this negative, I have to subtract 180 degrees from this phase angle. So I'm going to actually enter that as 7 angle minus 15 degrees. Now I need to subtract 180 rather than add because the range of these angles is restricted in Circuit Tutor as to the conventional range between minus 180 degrees and plus 180 degrees. So those are the ranges we normally use for angles. And so that's how you incorporate the minus sign. So it's very important to remember that negative 1 is the same as 1 angle 180 degrees. Okay, so that should finish those equations. Let's check those. And those are correct. Now the next step is to, and that you see that these have been written for us now for reference on the screen. Sometimes you might, if you're using a smaller monitor, you might need to scroll to see some of these things. So keep in mind you might have to use scroll bars. Okay, so the next step is to cast these things in the form of a matrix equation. Not that we're really going to want to probably use matrix methods to solve this, but you could in theory do that. So let's just do that, and it's very simple. We just click the button here to copy the coefficients so we don't have to retype all of them. It's presumed by now you understand the origin of a matrix equation. So remember that this times I1 minus 1 times I2, and then there's no I3 or I4, but this would multiply I3, this would multiply I4, all that's equal to that. That's the first row, and so forth for each of these rows. So for example, the third row would be 8I1 plus J5I2 minus J5I3 plus 0I4 would be equal to 2 angle 0. So in a similar fashion, the matrix equation represents all 4 of these equations. Okay, so we'll check that, and that is correct. And now our job is to actually solve for the unknowns, which are at this point the mesh currents. And we might look at the sought variables to see what we're really going to need, which is, in this case, we need I1, but we also need I2 and I3. So we need essentially all these variables, with the exception of I4. And that might guide us a little bit in how we solve them. So we don't need I4. Now, in order to do this solution, as I said, you could, in theory, perhaps use MATLAB or an online calculator to do this. But since on a test, for example, you'd have to do it by hand, typically. And most calculators can't handle complex number coefficients in matrices directly. It's going to be best simply to use elementary algebra. So we're going to take the 2 more complicated equations, namely the KVL equations, and take these simpler equations here, which are just easily solved for one variable or the other, and use that to substitute into here to eliminate 2 of the unknowns, and thereby we will get a simple 2x2 system, which is very, very easy to solve by elementary algebraic methods. And remember that when you're doing algebra with complex numbers, you do it exactly the same way you would do it with real numbers. The only difference now is you have complex coefficients in your equations, and you need to do, of course, complex number arithmetic, which will typically require a calculator that can do that readily. Okay, and again, your instructor may ask you for your handwritten algebra if they want you to turn that in. If not, it would be a good idea just to keep a neat record of that for yourself in case you want to review later how to do the complex algebra, in case you start to forget about that. Okay, so now we have the form in which to enter the 4 variables. We could, in principle, skip this and go straight to the sought variable equations. It does permit that, but since we need 3 of those 4 anyway, I'm just going to check all of these first. So we're going to do the algebra now on paper for convenience. And, sorry, I meant to do that. Okay, so, and, oh, well, I need to scroll over first. Okay. So here are the simplified equations. So what I've done is I've taken the third and fourth of those equations, which are the KVL equations, and the more complicated ones, obviously, compared to the first 2. And I've just copied those over. So we have the 8I1 plus J5I2 minus J5I3 equals 2. That's the, this equation, or the matrix row, either one. And then the second one is written below it, the negative J5I2 plus J5I3 minus J8I4 is equal to 7 angle minus 15. And I just abbreviated the 2 angles 0 by 2 in rectangular form, just for convenience here. Okay, and then below that, I've written the 2 constraint equations, which again are just copied from over here. The I1 minus I2 is 5 angle 180. And just for convenience, I wrote that as negative 5, because in rectangular form, that's what that is, remembering that 1 angle 180 degrees is always negative 1 in rectangular form. And then I3 minus I4 is 7 angle minus 105. So I have those equations. And again, my goal is to solve these. And if I look at it, probably the best things to eliminate would be I1 and I4, since the I2 and I3 are in both equations. And also we need I2 and I3 for this calculation here. So that's probably the best strategy. We don't need I4, so that would be a good one to eliminate. So therefore I've solved here for I1 just by adding, of course, I2 to both sides there. And then here I solved for I4 just by adding I4 and subtracting the 7 angle minus 105 degrees here. So now I'm going to take these 2 solutions, which are very easy to obtain, and solve those, or rather substitute those into this equation. You notice the arrow here shows me what I'm doing. So I have the 8 times I1, and now I substitute this value of I1 bar. The bars just indicate they're complex numbers here. And so I have 8 times that, and then I have the plus J5I2 plus minus J5I3 as originally equals 2. And now I want to simplify that because now I have multiple I2 terms. So I again want to put that into a simpler form. So I just notice I have 8I2 here and J5I2 here. So that just becomes 8 plus J5 times I2. And then I have still the minus J5I3 bar. And then now there's a constant here. This would be negative 40, multiplying that out. So I just add 40 to both sides, which makes the right-hand side 42. Again, I want all the constants on the right-hand side in the standard form. So this would be the standard form of that equation after substitution. Then I'll take the second equation, and again, I'm going to substitute. In this case, it would be substituting for I4, because I1 doesn't appear. So I have the negative J5I2 plus the J5I3, just copying those, minus J8, and now that's where I put in the I4, which is, again, from up here, the I3 minus 7 angle minus 105. And then again, I want to simplify this after substituting, so I see that now I have 2 I3 terms here and here, and so I have the minus J5I2, and then the I3 terms, I have J5, and I have minus J8 coefficients, so just adding those mentally gives me negative J3 I3. And then this constant term, I have minus J8 times minus 7 angle minus 105, a lot of minus signs there, and the 2 minuses will cancel, and giving me a J56 angle 105, which I subtract from both sides. So now I have 7 angle minus 15 degrees minus that J56 angle minus 105. I just multiplied those in my head just to save writing. Okay, and then now I would need to evaluate this difference on a calculator. There's no other way to really do that. So I guess I can just demonstrate that briefly on my TI-84 Plus calculator emulator here on the screen, just to show you how you do a computation like that. So the first thing you need to do always is to check that you're in the correct mode. You can't be in real mode here, or you won't be able to work with complex numbers and get the correct answers. So I've already selected polar mode since it's probably just as well to use polar mode. It doesn't really matter at this stage, but so I've just put it, and if you weren't in that mode, you would go in here and come down here and select the polar mode, which is over here. I've also selected, since I'm using polar mode, I want my answer in degrees because that's what Circuit Tutor ultimately accepts. So I've put it in degree mode as well. Okay, and I've also predefined, as I normally do, this variable e. So I've stored into that little e, like this one here, to the I pi over 180. And what that does is then if I raise that to the power of an angle in degrees, that will automatically convert the argument into radians. Because remember that this calculator, or like a TI-83 or 84 for that matter, have the quirk that they will not accept the arguments of complex exponentials in degrees, even when you're in the degree mode, which seems rather strange. And again, it's just kind of a sort of a flaw in the design of this calculator, if you will, or a quirk anyway. And the TI-89 doesn't have that issue, so you wouldn't probably need to do that on an 89, but in this model you do. So I've already defined that, as I do in the complex number video that you can look at. So let's do the computation then. So that would be 7, let's see, so we had the 7 angle minus 15 degrees, so I'm going to have 7, take that e, raise it to the power, and that's very important to raise it to the power, negative 15, and that was this part, minus J56, so I'm going to go minus, and I'm just going to click I down here instead of J, because they don't use J, and again, that's the decimal point key there, and then I do the 56, and then that's angle, so then I use the E variable again, raised to that power, negative 105. So that's this expression, and then I just click enter, and that gives me a number. It turns out, and you could have actually seen this in your head perhaps, that I, or if you wish, minus I actually has an angle, phase angle of minus 90 degrees, and so basically when you multiply that times this angle, it ends up giving you something that would also have an angle of minus 15. So it turns out, with the overall thing with the minus sign actually, so it turns out to have a simple result of 49e to the 165i, which means 49 angle 165 degrees. Again, because I'm in the degree mode. You've got to be very careful about the mode you're using in the calculator. A lot of people make mistakes because they mix up degree and radian mode. That's the most common error probably that people make, that and missing parentheses. Okay, so I've written that here. So that's that formula simplified. And okay, so now I have that form, and then I'm going to bring this other equation down here just again for convenience, rewriting it here. So we have the 8 plus j5i2 minus j5i3 equals 42. And now I want to combine these two equations to eliminate one of the two variables. And the one that looks like is easiest to eliminate would be I3 here. It doesn't really matter which one I do. So there I can just multiply by a simple real number, since clearly if I multiply by 3/5 here, that's going to make the negative j5 become negative j3, which is the same as this. Then I can just subtract those two equations, and that will get rid of the I3 term, leaving me with only I2 to solve for. And so I have to multiply the entire equation by that same constant of 3/5, or in other words, 0.6. So I've done that here. So let's do that subtraction. So we just have the negative j5. I2, of course, the I3 terms will be gone, so I'm not even including those. So we have negative j5, and then subtracting 8 times 0.6 is 4.8, which we can do in our heads. And then we have minus j5 times 0.6, which again, that's easy to do in your head, is minus j3. Just since 5 times 6 is 30, that would be 0.6 times 5 would be 3. And that's the I2 coefficient now. And then the constant, I have the 49 angle 165 minus the 42 times 0.6, and that you can quickly work out in the calculator, is just 25.2. And then again, we could just enter that number in the calculator, which I think I'll skip for right now. Well, maybe I'll just do it quickly. So that's 49, and again, I'll use that E key to the 165. and then minus 25.2 is a real number. And that will give me this answer, which is to 4 significant digits. And again, it's always good to have at least 4 digits here just for the sake of accuracy, because round-off error does tend to crop up very easily in complex number calculations because of the additional degree of freedom when you have a complex number. So we have 73.63, angle 170.1 degrees. Remember, this is in degree mode. Okay, so then I just combine this now. Combine the minus J5 and then minus J3 becomes minus J8. Still have the negative 4.8. So now I would just divide this number by this coefficient. So I can just use divide that previous answer. Now, I could not retype this in that form because, again, this calculator won't accept things with numbers directly in the degree mode. So that's a quirk. But if you use the answer, it does work because it stores it internally in a different format than it displays it. So it does work when you use the answer. And we'll divide that by, and we need parentheses, of course, here to get the right answer. So we'd have negative 4.8 minus J8, so we'd minus alpha I8, close parenthesis. Oops, I made a typing error there, looks like. So that should have been I. There we go. And that minus 4.8 minus I8. And we enter that. And so we have 7.892 angle negative 68.95, which I've copied down here. Okay, so that gives us I2. And next we want to solve for I3. So I can do that by using either of these two equations here. And I've just used the second one. Doesn't really matter. So the I3, basically I've solved for I3 by subtracting this, because I2 is now a known quantity. I've subtracted that. And I'm not using this, the minus or the multiplier here. I'm just using what's inside the bracket right now. So I take the 42, subtract off 8 plus J5 times now the known value of I2, which I just computed here, and then divide all that by the coefficient of the I3, which is negative J5, and that will give me the value of I3. And so let's see, I've got that value. I could just multiply that times negative parentheses the 8 plus J5 and then add to that the 42. And of course, using our using the order of operations, the multiplication will precede the addition, so that will give me the correct answer. I don't need to use parentheses, although I could. It wouldn't hurt anything. And I'll just get that answer, which is the numerator, and then divide that by, now parenthesis, minus I. Oops, I didn't mean to do that. So I meant second I there. And I forgot the minus sign, so let me try that again. So I meant minus I5, close parentheses. Okay, again, I have to have those parentheses, otherwise I would just be dividing by minus 5 and then multiplying by 5 based on order of operations. So the parentheses there are absolutely mandatory. And that would give me the value then of the I3, which is 9.611, angle negative 158.6 degrees. And again, we are in the degree mode. That's very important to always monitor that. Okay, and then finally, for I1, I can go back to my original expression up here, negative 5 plus I2 bar. So I've just put in negative 5 plus, and then I substituted this value of I2 bar here. And I think I'll skip that in the interest of time here. That works out on the calculator to 7.677, angle minus 106.4 degrees. And finally, I4 bar, that comes up here. We can use the I3 minus 7, angle minus 105. So again, just entering those similar to what I did before, we can compute that easily on the calculator, and that would give us 7.844, angle 155.5 degrees. So now we'll go back to Circuit Tutor here and take the form and just enter those numbers into the form. So the I1 is 7.677, oops, 7.677 angle negative 106.4. And then the I2 bar was going to be the 7.892, angle negative 68.95. And then the I3 was going to be that 9.611, angle negative 158.6, and using 4 digits for accuracy here. And I4 is that 7.844 times the 155.5. Oops. Okay, and so that should be correct, assuming I didn't make any typing errors there, and I'll just check quickly. I believe that's correct, so we'll check those answers. Those are correct. And now the last step is to use the sought variable equations, which are these, to compute the sought variables. And we'll go here. And so, for example, for the V naught, I would just take the negative of this value, which is very easy to do in the calculator. Of course, you could just add 180 to the phase angle, would be a way of taking the negative of that, and then multiply by 8. And of course, when you multiply by 8, that's just 8 angle 0, so that will multiply the magnitude rather than just the, that won't change the phase angle because you're adding 0 to this. And likewise for I naught, there we would just subtract the I3 minus I2. Again, would require, of course, a calculator. In the interest of time, I'm going to skip showing that entered in the calculator. But to give you approximately these values, maybe a little bit off, just rounding, but it'd be approximately that. And then we'll check those answers. And those are correct. And the final thing would be to express the desired sought quantities in the time domain. That is to do the inverse phasor transform on each of those things, namely the V naught and the I naught. So now we have the blanks here to fill in. And remember that if you weren't doing this in Circuit Tutor, you would have to remember yourself that the inverse phasor transform always involves a cosine function of time. And of course, you have to have the time variable in there. If you didn't have time, that would be manifestly incorrect because it wouldn't even be a function of time. It would not be in the time domain. And I have noticed a lot of times people do forget the actual variable, and that's, of course, critical to include. So here it's putting in there for you, but it's very important when you're doing this by yourself on an exam, for example, that you would put in the time variable explicitly. Okay, so that for the V naught, well, actually for both of them, we need the thing that multiplies the t, which by definition is omega, not f, right? Omega is always what multiplies t. And omega, remember, is 2 pi f. So in this case, we're given f in kilohertz. And remember, hertz is not a unit of angular time frequency. That's a unit of linear time frequency. So in omega, therefore, would be 6 pi kiloradians per second. And in order to get the number for that, we'll just use the calculator. So 6 pi times 1,000, I guess, for the kilo. And so that would be, I'll just call it 188 is good enough, 188,000. We don't want to have too many digits there. Let's see, that was 18,800. Let me just double check that. Oops, calculator. Yeah, 18,000. Okay. And this other one, of course, would be the same, 18. And then for the V naught, we just put in our magnitude that's from down here. So that would be 61.42. And that angle is the 73.61 degrees. Everything's always in degrees here by default. And I naught is a 12.4 amplitude, and then the phase angle would be the 161.8. Okay, and then the appropriate units, of course, if you're doing by hand, you've got to make sure that you put the units on these quantities or they wouldn't be treated as being correct. Okay, so let's check that. And those are in fact correct. That's been printed on the screen. And And that does complete the problem. Again, you do have available a detailed explanation of, for example, the KVL equations that were given to us and the slot variable equations, in case you weren't sure about that or had to guess. So there, again, you can get very detailed explanation of the KVL equations. If you wanted to click this button, or if you need more explanation about constraint equations, you can click this. It's showing you the super meshes that were actually used, and then there's another one here that was used to find the other equation. So there are actually two super meshes in this problem. So that does complete this problem.